Hello, everybody. This is Meisam. I am a researcher working at a smart thermal energy system in thermal energy section department of the Construct, Technical University of Denmark, and going to have a presentation about our activities in the CO2inloop project, optimization of district heating systems with CO2. At the beginning, it is good to have a short introduction in CO2-based energy systems. Determination of the temperature of the network is important because the operating temperature strongly affects efficiency, pressure levels, heat losses, equipment size, safety, and overall system economics. So the gap here is the lack of system level assessment and the network optimization. Thus, we are going to find the optimal temperature for the network during the annual operation of the system. Here in this slide, we can see the schematic of the work. We have 5 main components. There is heat source. We have centralized heat pump, the network, the decentralized heat pumps, and the customer or end user. And the heat flow here is defined that the heat is absorbed from the heat source, then it upgrades it to a higher temperature at the network temperature level. Then the heat is delivered to the network and transferred to the endpoint where the decentralized heat pumps receives the heat and upgrades it again to a higher temperature and then deliver it to the end user. For the case study, for the 5 consumers here on the map, we can see they are located in neighborhood at different distances from each other. And we can see here the demand and also the profile of the temperature through the year and the demand, both the space heating and the domestic hot water need. Then we have the methodology here in this slide. In this slide, we have an overview of the computation process. This flow chart visually summarizes the step decisions and processes. Taking in input variables, ambient temperature, which is the heat source temperature, and the required customer temperature, which is defined the heat sink temperature, and also the temperature of the network, which should be defined between the heat source and the heat sink temperature. Also, we consider the standard pipe size by defining the maximum allowable material stresses and the allowable velocity of the vapor and the liquid. We also take into account the amount of heat transfer between the pipes, the ambient through the soil, and the thermal conductivity of the soil, considering the friction of the fluid inside the pipes as function of the Reynolds number and the relative roughness. We do the calculation and we calculate the pressure drop and the other properties like the temperature, pressure, sizing the system in a try and error methodology. We use these algorithms, as I mentioned here, for the calculation of the properties of the cycle. Then after implementing the algorithm described before in the last slide, then we define for each specific temperature of the network. We can have run and simulate the system and investigate the electricity expenses of the system. We could perform the optimization algorithm on that algorithm. Here we defined the operation expenses or the electricity price as the objective through the year to see how the system performs and how we can compare the scenarios. From the figure here, we can say that we can observe that the system response is not monotonic, is not uniform with temperature, and we can have more discussion in the next slides. What we have here, and we can see, is that we set the temperature of the network in a specified range. Here, for this specific case, we defined the range between 271 to 280 Kelvin, and the simulation is performed. And the result can be seen here. Here we have the diameter of the liquid and the vapor lines for different temperature for the network. We can observe that when the network temperature increases, the diameter of the liquid pipes increases, while the diameter of the vapor pipes decreases. Also, about the other results, we can see here that the COP of the unit is maximized when we have the temperature 276 Kelvin, and the heat transfer between the decentralized heat pumps and the network is minimized in this case. In addition, we can see the heat loss from the network also is minimized for this temperature. For this comparison, before that, I need to say that we should identify the heat source type. So we defined two cases here, and in one case we got an air source heat pump, and in the second case we defined a water source heat pump, and then comparison is done based for different cases. Here we can see that for the mentioned cases, case 1 and case 2, air source and the water source, we can see the results of the optimization for the whole year. And what we can see is the optimum temperature of the network for each hour. And we can see from the second case where we have water source heat pump at the central station. And the temperature of the heat source for this case is relatively constant during different hours because connected to the water heat source. We can observe that in 75% of times, the optimum value for the network temperature is about 276, and it is constant at that temperature. And when we have air source heat pump, the case 1, we can see that the variation of the temperature is, we know that when we have the air source, the variation of temperature is higher in this case, and 28% of the times we see the temperature 11 or 12 centigrade, which is about 284, 285, yes, Kelvin. We have the optimum value for the network temperature when we have air source in that case. And we can conclude here that if we use the water source system, because 75% of the times the optimal temperature of the system is fixed, so we do not need any more control system for the temperature of the network if we can identify the right temperature and the proper temperature of the system. Finally, it is a good idea to have a discussion a bit about the logic behind the fluctuations of the objective, the fluctuations that we observed in electricity price, and why this happened. I do not want to go into the details too much, but just a short discussion would be good, that we know the temperature of the network directly and also indirectly impacts on different parts of the system, and we can see that when the network temperature changes, we know it can make impact on the end user temperature or the pressure of the network. It can make impact on the performance of the central and decentralized heat pumps. Also, the mass flow rate of the CO2 and the density of the working fluid and the diameter of the pipes and the heat loss and the pressure drop. And finally, we will have, because we know that we have a lot of pipes in the network at different locations with different sizes, and when we want to do the calculation, we should do the calculation pipe by pipe, from one pipe to another pipe. Then when we want to calculate the outlet temperature and the outlet pressure, or the pressure loss for each pipe, or the heat loss pressure there, or the heat loss for each one, then in that case these parameters are very related to the network temperature. So, but among all of these parameters, the sizing of the pipe is a significant parameter affecting the behavior of the system, because when we optimize the temperature in the network, the hydraulic design of the system, when I say the hydraulic design here, I mean that the pipe size and the schedule of the pipes, I mean that the thickness of the pipes could introduce some discrete jumps in the calculation for the pipe size. Anyway, these jumps that I mentioned here, that we have between the standard pipe sizes and the schedules of the pipes, could make impact on the flow area, the pressure drop, the amount of the energy that we consume, and that would be the reasons that the system responds non-monotically with the temperature. It was my presentation about this, and this is the team at the DTU and at the Smartest group. And if there is any question, you can send email or we can have a discussion here. Thank you.